Hello, this is the first session of Computational Plasticity, where we are going to look at other nonlinear problems, in solids. So you have seen phase fields, where is a first type of nonlinearity. We have nonlinear elasticity, okay, and this is like the second type of non-elastic deformations. The first one was with damage, okay, so it means that our our Young modulus is being degraded. In this case, is another type of inelasticity where it's not the Young modulus being degraded, but in fact there's a limit, like a cap, in the stress value. Okay, we're going to study because this was started in the 50s and 60s, so rigorously studied, but it was happening in materials much and observed much earlier. So in fact, you have that called plasticity because it's what plastics do, but in fact it was observed also in metals, so that they plastify. Okay, so we're going to see how we would in fact treat that numerically, how to model. So we're going to visit first the analytical expressions of the model and also see how we can compute actual values. So we're going to see first like the 1D problems, okay, first and compare how elastic response would be versus a plastic response, and we would have also a one-dimensional or a toy problem where we can see observe the main differences. We will, in fact, emphasize the main difference between the elastic and the plastic formulations. How to, we'll see that these are in fact differential equations, but with some constraints. So it's a set of differential algebraic equations that we are going to numerically treat with some set of methods that we will extend then later on to more than one dimension. So first of all, this is happening quite, well, hopefully not quite often, but not only in some, some types of behaviors are observed in not wishful situations like this type. We want to see how it responds. Okay, we know this happens, so we want to know how things are deforming, or where the engine, for instance, in this case, where the engine is going frontally to the driver, or in a more wise manner, so it should go underneath the driver, for instance. So now cars are designed such that so when they are subjected to an impact like that, the engine goes underneath the driver as much as possible, of course. Okay, so in order to diminish a bit the effects. So you want to control, and so in order to that, you need to model. So this type of large deformation. So we see here it's like large deformations. Okay, we may have cracks as you have been modeled in phase field models, but we have other types of deformations that are not necessarily cracks. So you may have no crack indeed, but still things are non-linear. And by non-linear, we mean that things do not go back to where they were when there is no load. Okay, we see another simple case. So we give a detailed test like that. So we have some screws that are here attaching to different pieces. So in fact, in linear elasticity is that you pull these two rods are being pulled, and you would be along this branch. So you have the displacement, and if it's displacement control, it means that you control this branch here, and as you pull, so you have that the force that you need in order to put them apart at a given distance. So it's given by this slope, and that would be like the stiffness, okay, of this system. Okay, so for a given displacement, I have to increase a given force. Okay, so this would be in the linear regime, where if I remove the load, it goes back to the origin. So it means no load, no displacement, right? And there's a constant of proportionality between the two. We can say that this stiffness would be something similar to the Young modulus that we will have, and my force in the linear regime would be proportional to my displacement. okay, and we can write them in that linear elastic regime, okay. We will have something like that, and we can write it in linear of rates also as well, okay. So we have a slope here, and we divide everything by delta t, and we have this type of regime. If we keep pulling in this test, so it turns out that you have a plateau, there's a maximum force, and for instance, then when you try to pull it a bit harder, so your force does not increase linearly anymore because something has happened here on that screw, so it has gone out of its initial position. So plastification is like locally and in a microscopic level, not at this level that we have here, but inside the material, things are relocated. So you have like so that you have recollocation a little bit of the microstructure. Okay, in this case, the screws that have gone out, and in fact, so you have a different slope at some moment, which is much in fact slender and softer than it was initially. But one of the main characteristics of plasticity is that once you have reached that point, for instance, so you try to remove the force, you don't go back to your initial position. Okay, so it does mean that it does not go to zero force, zero displacement, what we had in this law. So for nonlinear, okay, so in fact we see that this is not anymore true. Okay, so increment of load is not equal to an increment of displacement, because if we remove, we go back to that branch here. Okay, so this means that something has happened, and inside, so the microstructure is not, so it has plastified, we say, and then goes back to another different branch and another slope, also as we see here. If we want to keep loading, so in fact the new in that regime we are like in linear, so in fact there's a shift with respect to the origin, and we are in this different regime. And we keep loading, we will go up to this moment, so it means we keep pulling up to the moment that the screws are again tight and doing some force, and at that moment, so we keep having another loading branch like here. But it's still non-linear because it doesn't go to the origin, it goes through a branch. And also if we want to unload at that moment, so at that point, so for that displacement, we will also go through a different vertical, nearly vertical branch. Okay, so the stiffness have changed in that sort of unloading regime. And if we keep then loading, okay, on that branch from here, so we would be going down, we go nearly, okay, to zero force. Okay, again we keep loading again, and that so we go through the same branch that we were up to a point. Okay, we would keep trying to load, but there's a maximum value of the load. From that moment, maybe one of the screws have gone out, okay, or more than one, and in fact we keep adding some displacement, but in fact the load does not increase, there's a softening. Okay, so that would be like a hardening branch that we will have along this okay, this interval of the displacement. But from those displacement here, in fact we have some softening, because when we have a relation between displacements and forces is that for any increment of displacements we have a decrease on the load. So this is like a softening behavior. The more I impose a displacement, so the higher I go on the right, okay, so the lower it becomes the load. And I keep going, so at that moment probably there's fewer and fewer screws to a moment that they are completely detached. So here these two have become completely detached, and I keep this adding displacement, but in fact I have no load, no resistance, because it has broken. So we are going to focus not on this whole okay, all this history, okay, of loading and displacement, but rather something more simplified, something like that. We are going to work on a simplified model in order to reproduce material behaviors like that. but not with the screws, but in our continuum approach. That's how we know how to model so far with elasticity and phase field models. So we're going to include this, the idea that first of all, that there is a maximum load beyond which things are becoming nonlinear, and the idea that if I unload, I go through a different branch. So this is one example, okay, where this is not designed. This is another one where this is not designed. We see here, this is a crane. It was supposed to be straight, okay, and because this has gone some plastification on this hinge that has been created, it has bended very undesired conditions. So this is an accident, but sometimes you really, if you can control this plastification, is something that is beneficial. Like in this case, you have a mold, like a cast, and then you blow, and this material with some temperature control manner, so you can keep blowing and change the shape, okay, with there, so you get advantage of this plastification. So plastification means that if I obtain some pressure and I see, okay, what would be my length, so in fact I would keep increasing, okay, maybe it's linear, but immediately maybe non-linear, and if I remove my pressure, in fact it would not go to the initial length that I have here, okay. So this, call this the persistent length that we have, so would be even if I remove my pressure inside this mode, so in fact I would keep remaining a certain let's call it this length or persistent length that we have here. This is like the plastic. We can also denote as a plastic length because it's a remaining length, so it doesn't go back to my, that would be going back through that curve would be non-linear elasticity. If I go through another curve, would be going back, and this would be a signal of plastic deformation. Plastic deformation means those that remain for zero loading. Okay, if we keep blowing, in fact, with this deformation, of course, we remove the air pressure, and this is the final shape. So maybe beneficial if we have a cast and we want to create a model of a bottle, for instance, here. So we can, this bottle is a result of plastic deformations on that initial material in that domain. Okay. So it can be beneficial. There are other many beneficial situations where you create a hinge. You may want to have to create shapes of like a plastic clip as well. So the plastic clip was initially something I think, the paper clip, I mean, so something like that. Initially it was a straight, okay, straight rod, okay, metallic rod, that through plastic deformation you create a plastic clip. Okay, very simple one as well. Okay, so let's go into the model, how to represent that with our formulation that we have so far, and we will focus on 1D, okay, representing as we have done in those examples with a deformation epsilon. Okay, this is the observed the total deformation that we see in the material, and these are the stresses. Okay, imagine that this is 1D, so we have two scalars. Okay, so the slope will be like our Young modulus, that's the stiffness, and we go up and down through that line. If it's a line and E is constant, so it would be linear elasticity. Okay, and it's elastic because we go back through the same curve. So that would be nonlinear because the slope that we have of, in fact, epsilon dot that we have, it's something that in fact depends on my stress value, depending on the stress or on the strain values. So we may have, instead of that, sometimes for formulation is better written in terms of epsilon. Something like that by my epsilon dot. So this Young model is not constant here, but may depend in fact in the where is my displacement, for instance. But I'm going back, so it's elasticity because we are going through the same curve here. All right, so where all this is elasticity, okay, no plastic behavior because for zero, this nonlinear representation that we have here satisfies that this is going through the origin. So it means that if I have epsilon equals 0, this means that my stresses are also equals to 0. Okay, so everything and through the curve, and there's a one-to-one relationship between stresses and strains. Okay, so we have a stress strain curve and what is happening in steel, for instance, and that's why it was mostly studied in the 40s, 50s, in fact. So we have an initial branch and then a softening, a sudden and a plateau, where in fact we can keep increasing my strength. We will have like a test like that. So I keep pulling, so it means imposing a certain strain, and this is a touch that I have here, and I'm measuring like the force that I need in order to impose this strain. So we see there's a plateau, so it means I keep pulling and nothing, no stresses are being added, are being measured, and we may have a final hardening curve here and then a softening curve, right? So this is more or less like the stress strain curve for steels, like a standard curve with these different relative reference points that are normally done on a test. Then if we go and we see what we want to simplify the behavior we have seen for those plastic regimes, okay, what turns out is that we don't go back at that point. For instance, if we keep increasing, we go through that curve, but if from that point I go down, I don't go down through the same curve while I was loading. Loading means going through epsilon larger than 0, and that would be my loading branch. Okay, if epsilon is lower than 0, that would be unloading. Okay, so I don't go back through the same curve I was, but instead I'm going through a different curve. Okay, that looks linear, so it's like another sort of linear behavior, but is not going or convergence toward the origin, but instead is going parallel, like for the initial curve, but okay, slightly shifted with respect to the initial point. So this goes through that branch, apparently linear branch, as far as we don't reach the initial points of my loading curve, right? And that's how we would have we lose this one-to-one behavior. So for one plastic or for one total strain, so I may have different values of my stresses depending if I am on my loading regime, okay, or I have gone through an unloading. So it's history. We see it's history dependent. Okay, so that we lose this relationship, but we can have on respect to the rates, we can have a one-to-one relation with respect to the rates, okay, that we have, and this may depend as well onto my current strains. So a simplified model of that behavior we have seen would be, let's have with the straight lines instead of these non-linear curves. So having a straight line where you have full linear behavior up to a maximum stress value, okay, beyond which, okay, stress can still increase, but with a different slope. Okay, so something has happened inside the material. Okay, so we have that the microstructure have changed, so they have the so-called dislocations inside the material. So we have a slip of one material with respect to another. So we have discontinuities, but we model them through a continuum model that behaves with those different regimes. So that would be beyond this yield stress. This is called like the yield stress, beyond which we lose the linearity. And then we have, beyond that value, we change the slope, and we have a different slope, and we will have that this, okay, elastoplastic modulus is smaller than my initial elastic modulus, okay. And whenever I'm unloading from any point on that branch, when I have gone beyond this yield stress, so when I remove the stresses, then this would mean that I'm going parallel okay, we will simplify our model and then have an unloading behavior going parallel to the your modulus. Okay, we will simplify in that manner. That will make our life much easier later on. Okay, if I keep going down up to 0 stresses, so I'm loading my domain. Okay, no loading boundary conditions, so I leave it free. So I would then reach a given strain that we'll call the plastic strain. It's irreversible in the sense that even if I remove my stresses, I will not recover this strain, okay, for 0 stresses, okay, because it has plastified. And this elastic strain is the under this loading and loading branch. I keep increasing and decreasing this amount of strain, which is called the elastic strain, the reversible strain. So in total, at that point, let's call this my point A, and that would be like my point B. So at B, my total strain is the sum of this plastic reversible strain plus the elastic reversible. So if I go back to my point C, it means that my stresses that I will have at C will be equals to 0, but still I have a remaining strength even if the stresses are equal to 0. Okay, and in fact my stresses at that point, they are proportional but only to the elastic strength. So we keep this proportionality of linear elasticity, but just bear in mind that we have this shifted branch here with respect to the initial linear branch that we have. Okay, so these permanent deformations that we have is what we observe so some of the applications. So in the car industry or aeronautical industry, so you start with a flat shape, okay, you apply some on the cast or some molding, and then you get a deformed shape. That's what you want to put in your in the chassis or or any shell that you want to build your car, your shape from. So you create some plastic strains. Okay, in this case that would be equals to 0. Sorry, I mean equals to 0. Okay, and at that moment I create some I apply some stresses. I'm creating some plastic strains, okay, which may be okay larger than 0. See, anything may happen, okay, but I have created some plastic strains. So in general, you don't know which are well located, but what you care about, okay, in industry many times is about the shape. This is what you aim for, and you want so that also that your stresses are as low as possible. Okay, you always want to satisfy this. We said that this in statics, this divergence of sigma equals to 0 is true for any material, and linear, non-linear, and that's even true for plasticity. So this is what we needs to be satisfied everywhere. But this does not mean that your stresses here, even if you unload them for that deformed shape, you may have that the stresses are different from 0. These are called the stresses that you have on the when you leave it free. These are called residual stresses. Residual stresses because you're not applying any loading at the boundary. Okay, so you have homogeneous conditions at the boundary. Okay, but you have internal stresses. So they are self-equilibrated. They are called, but they are there. Sometimes they are beneficial because you get the shape, okay, that you want, and you want to diminish them also because you don't want the data too high. You want to have them controlled, but sometimes they are beneficial in the sense like you have in the windshield, in glasses, in cars, for instance. They have some internal stresses. So when there's a small fracture, these internal stresses they create and they break in small pieces due to these internal stresses that they have. Okay, otherwise you will have larger pieces. So this is designed but it needs to be, in fact, control the amount of internal stresses that you have, right? So, this is our simplified, going back to our 1D model. This is the model we want to build. It must be able to represent some different regimes, unloading and unloading branches like those that we have here. Okay, so there's a different type of plasticity. This is a perfect plasticity, which means that this slope is flat, so there's a maximum yield stress, beyond which the material is unable to resist. So you can keep imposing larger and larger deformations, but the stresses will remain constant. You may have some hardening, okay, so hardening meaning that stresses keep increasing but a different slope. Okay, we've seen that those regimes also as well. You have rigid plastic, so it means that you get rid of the elastic branch, initial elastic branch, because you only care about the plastic deformations. Okay, and this is relevant. This type of analysis is called limit analysis. So it means depending on the distributions that you have on a domain, okay, like that, and you have some loading, so you just care about the plastic deformations, not how elastic, because the elastic deformations in general, they are much smaller, okay, when you have the plastic deformations. So when things, the plastic deformations that you have, or this epsilon that you have, any epsilon that you have in this case is plastic, so imagine that your plastic deformations concentrate here. Okay, so this cannot bear higher stresses, so there's a maximum force that you can have in your domain. This in soil mechanics, this is much used, this limit analysis, and what you care is about the bearing capacity of the bearing capacity of a domain that you have where your plastic strains are concentrated. So depending on the distribution of your plastic strains, you may have what is called collapse of the structure. So this is different. My epsilon sigma is something that can be seen for each point. If you model instead the maximum force that you can include here, and you measure the displacements also that you would have here. So instead, you may have a maximum force, and then when this distribution of stresses is fully on that domain, then maybe it's a maximum force. Okay, beyond which you reach and then it collapses. Okay, so in soil mechanics, this is very much used. We won't go into this type of behavior or this analysis, which is another simplification. We will care mostly about first about this perfect plasticity, and then introduce some hardening as well. This softening, okay, it's relevant also for composites, okay, composite materials, where in fact what is happening during the softening branch is also relevant, because you have some residual still remaining stiffness in the material while it's being softened. Okay, so this is also relevant in some applications, but we won't also look into this type of problems, and we go first about perfect plasticity and then hardening. So let's go into our initial. This is a reference where this is taken from, and you can have a look at more detail. Okay, so it's a 1D problem that represents very similar to what we want to model. So instead of a continua, we look at a spring with a stiffness K. Okay, so Hooke's law is telling us that the force is proportional to the increment of length that we have for that spring. Okay, and that would be an elasticity. We will use that as a comparison that we will have in continua. In continua, we work with stresses and with the strains. Okay, so would be very similar we will have in continua if we have the force divided by the area. Okay, this is the area, okay, of the cross section. Okay, so we have this cross section, and the stress is the force per unit of surface. Okay, so if we take a spring that has a cross section equals to unit, so we can identify the stresses as the forces. Okay, so we think as that spring similarly to what we have in continua, in fact, with a cross section equals to 1. And our strains is a relative, it's non-dimensional, and is a relative increment of length in linear elasticity with a small deformations. So we have increment of length with respect to my reference or initial length. If my initial length, we take it equals to 1, okay, so our strains can be identified by the increments of length. So we will work with a spring like that, okay, where with unit length and unit cross-section. And we may think as a 1D elasticity problem in the same manner. So our K, which is the relative, the ratio between the forces and the increment of length for this problem with unit length and unit cross-section is equivalent to the stress divided by the strains, would be our Young modulus. That would be for linear elasticity, spring system or in continua equivalent to spring with unit length and cross-section. Now, let's try to think of that spring equivalent to continuum with plasticity. So this spring is not anymore fully attached on my right hand side, but instead we have a frictional device. You can think of so this is attached but with some addition to that block here, and whenever I'm pulling, this follows and the spring deforms together with that device. So friction allows me to pull in the same manner, but after a given stress value that I have means that the relative deformation of the spring and this frictional block here, okay, may not be the same. So I don't have the same displacement for the two, but beyond a given value. So when my stresses in absolute value are larger than a given threshold, then this block slides onto the spring. Okay, when the stresses are below this value, then there's no sliding and the two move together. Okay. So that would be very similar. That would behave very similar to what we have represented and we wanted to show before. So it means that, okay, so if I have a given strain, so whenever my stresses are below my yield stress, things move together and I have the elasticity of my spring. At that moment, okay, so the spring, when I keep increasing my stresses beyond sigma y, this starts to slide and the spring is still stretched with this stress value, but all my strains are not due to the spring lengthening, but instead for the relative slide. So that would be equivalent to this is sliding, okay, with a given amount, which is this epsilon p. This is a relative slide of my frictional device, and this has been pulled a given amount, epsilon e. The total strain, okay, is equal to the sum of the two. Okay, I have reached that value, so that will be my epsilon e, okay, and that gives me the value of sigma y. Okay, so it means that my sigma is equal to my stresses by epsilon e. Okay, and that will be my value that I have. And throughout this branch, I do have this behavior, sigma is equal to the Young modulus by epsilon e. Okay, and this is true at that point and at any point that I have here for different epsilons elastic. So that may be another value of elastic strain, and I may get another value of stresses. So in fact, this is true everywhere where I'm taking into account not the total strain, but instead just the elastic strain. Okay, at that point, I have this value of my elastic strain plus, okay, my elastic P, the same that I have here. Okay, and if I look at the stresses, in fact, they behave like that. Assuming that at the moment that it starts to slide, my stresses are the same. The spring does not shorten due to the relative slide on one and the other. Okay, so if we have that behavior that the strains are the sum of the two and my stresses are proportional to the elastic, I can describe my elastic strains as the difference between the total, what I see, and the plastic, that is what I'm not seeing, but I know that is there, the relative motion of the frictionless device with respect to the spring. Okay, so this is going to be my constitutive law. This is the important bit that we have, is that my constitutive law is still valid, but I have to take into account only the elastic strains. Okay, and with respect to what I see, my total deformations, I must then subtract from the total the plastic strains. Okay, this is the main mention for the whole plasticity. I have these permanent or remaining or irreversible strains that must be discounted in order to give my stresses proportional to the Young modulus. Then, which type of regimes may I have? I have my linear elastic regime, then which is linear elastic whenever the stresses are below the sigma y. Then I have my plastic regime, so it means that my stresses are constant, and throughout this this line is part of the curve of the stress strain, but throughout this path, what I have is that my constant stresses, so the modulus of the stresses is equal to sigma y. They do not change, although epsilon do change. Okay, this is positive, but what I'm having is that my elastic strains are equal to 0, and because they are equal to 0, it means that my total strains are just equal to the plastic ones, because this is the sum of the two. Remember that we have that the total strain is the sum of the two. This is true for the strains themselves and also for the rates doing the time derivative. So if this is equal to 0, then any increment that we have along this path is only due to the plastic strains. Okay. While we are on that branch, 3 and 4, then we may have that my elastic strains are different from 0. Okay, we will see what's happening, okay, with the plastic strains on that branch. Okay, so the spring contracts and the spring elongates up to that point, and we know that our stresses always must be, this is like a constraint that we have, that my stresses must be bounded by sigma y in absolute value. So my only admissible domain goes from here to here with respect to the stresses. Okay, and this is like a constraint. We call this the admissibility domain. Okay, which is any value of the stresses such that the stresses are smaller or equal to sigma y. And we write this admissibility domain as my stresses must belong to this admissibility domain. Okay, this is one constraint that we have in plasticity. I have imperfect plasticity. My stresses cannot go beyond these values. These are forbidden values. Okay. So it turns out that we are solving linear elasticity. So my stresses are proportional to the elastic strains together with that constraint. Let's try to formulate that into a little bit more rigorous manner. So my stresses must belong to that interval. So we define that interval as any value such that we describe to a function that is negative on that interval. So this is my stresses, this is minus sigma y, this is sigma y, and this is the interval, okay, where my function is smaller or equal to 0. So let's write it properly. So we have my values and my function, then in that interval up to here, okay, sigma minus sigma y that I have, okay, must be relative to negative. Okay, so if I would plot this function on that domain, okay, so for sigma equals 0 would be minus sigma y. Okay, and the absolute value, okay, minus sigma y would be equals to 0 here, okay, and this equals to 0 here. Okay, and from that moment, because my stresses cannot go beyond that value, is where my function would be positive. Okay, so I'm describing my admissible domain as the values where this function is smaller or equal to 0. Okay, so this is my admissible domain for the stresses. Okay, another way of describing that. This is called the yield function, and is the one that we impose for the stresses. So sigma must be such that f of sigma is smaller or equal to 0. Okay, and this is an admissible domain. Okay, all that was f is positive. Right, so we have another way of defining our, this is just defining our admissible domain through a function. Okay, that will is, because now the boundary of our domain is equal to the values of the stresses, okay, such that f of sigma is equal to 0. Okay, the boundary of my domain is these two ends here, where the stresses, where the function vanishes. Okay, and that's the boundary of my domain, and where there's where different different variables take different values. That's why I want to distinguish that. Okay, so whenever we are inside of our domain, at the interior of my epsilon is where we are going to have any plastic strains. We are in the linear regime. Okay, so it means with respect to our path that we have, so that we have the linear regime and up to that moment. But if we are except this branch that we have here, that's the linear one. Okay, and except this value, and the same happening here, except this value, okay, we are having linear regime. Okay, so this is fully linear. As far as my yield function is smaller than 0, it's just linear. Okay, whenever we are somewhere at the boundary, so it means that the stresses belong to the boundary of my admissible domain. At that moment, what we have is that my stresses, are equal to sigma y. Okay, because f of sigma equals to 0 means we know equals to 0. We are at the boundary, and equals to 0 means that the absolute value is equal to sigma y. So we are at these two ends that we had here. We are either here or either here. Okay, and here is minus sigma y. So we are at the boundary, and so at that moment we must have that my stresses are equal to sigma y, and we call this gamma, so the absolute value of the slip rate. So how much my plastic strains are increased. Okay, these are always positive, this gamma. Okay, and whenever sigma is at that top boundary, of my admissible domain, so we'll have that epsilon p is larger than 0. So and whenever we are at the other end, my epsilon p are going to decrease, and we call that this is equal to minus gamma. But gamma is always going to be positive. Said otherwise, my plastic strain rates are going to be like this: gamma is positive multiplied by the sign. Okay, when stresses are positive plus gamma, and stresses are negative minus gamma. A way to write that syntactically, right? Okay, so we are more or less having all the ingredients to describe our problem. Okay, first of all, let's see how we can determine this sleep rate, the gamma, which is the amount of sleep rate that we have in a problem. First of all, we always define so perfect plasticity that our gamma is larger than 0, and these two conditions. So necessary conditions that we must have is that always that gamma is positive, always my f of sigma must be larger, must be smaller or equal than 0. Okay, and because we know that gamma is only different from 0, gamma is positive whenever we are at the boundary. So going back to our drawing, we have that in here we have when we are moving on that boundary, we know that gamma is larger than 0 and f of sigma is equal to 0. And that boundary we have the same thing. Okay, f of sigma is also equals to 0 and gamma is positive. Instead, on that branch, we have gamma equals 0. We're moving elastically, epsilon p does not change, and my plastic strains do not change, but f of sigma is smaller than 0. So as a way of writing that is that gamma by f is equal to 0. This in optimization, we have a constraint. In fact, we have a constraint that f of sigma is small or equals to 0, and gamma plays the role of a Lagrange multiplier. Those familiar with constraints, in fact, a way of imposing the constraint is that we have a Lagrangian where we have this term. Okay, we are minimizing the total energy subject, okay, to that constraint to gamma by f. We may have that we want to minimize the total energy. Okay, and what we have in plasticity is sigma by the elastic strain. Okay, minimize this total energy that you have, but subject to f of sigma equals or smaller or equals to 0. Okay, this is equivalent when we work with optimization. This is equivalent of minimizing my functional that I have here, okay, the total elastic energy that I have, with adding a Lagrange multiplier onto here by f of sigma. Okay, so this is the extension of my my extended Lagrangian function where I add a Lagrange multiplier to that. And I know that because this is an equality constraint, so also gamma is subject to be different from 0 whenever f is equal to 0. Okay, so we cannot have the two different from 0. So when gamma is larger than 0, my function, my constraint is equal to 0. Okay, and that must be true because we are under, in that case, we are under the plastic regime on that branch. And whenever f is smaller than 0, then my gamma is equal to so it means that elastic branch. Okay, and here we will be in our plastic branch. Okay, in that case or in that case. Okay, and there is a persistency conditions as well that we can add, is that f can only change whenever, okay, can change the value whenever we are at the boundary and go to the elastic regime. This is equivalent to being on the top in our regime. So we are somewhere here, and f, okay, may change. So we know that at the boundary f of sigma is equal to 0, and for that branch we will have f of sigma lower than 0. So this is going to change, and it can only change whenever the plastic strains do not change. So we are going through that unloading branch, and this is equivalent, the condition that only when we unload an f can change sign whenever gamma is equal to 0. And whenever gamma is larger than 0, we must remain on the boundary of our admissible domain for the stresses that we have. Okay, so this is equivalent to, say, my gamma multiplied by f dot. This must be equal to 0. So whenever gamma is different from 0, it can only be positive. Okay, then it means that f is equal to 0. So we are at the yields and we remain on the yield surface. That's why it's called a persistency condition. And whenever f dot decreases, okay, so it means that goes from f equals 0 to a negative value. So we must have no additional plastic strains. So no plastic slip, no relative motion between the two. Okay, so we have these, in fact, these constraints. Okay, and when can they be simultaneously different from zero? This is forbidden, and this is the Karush-Kuhn-Tucker condition. Or also when they vary, when we have variations of f, there's also this persistency condition. All right, so in total, we may look at okay, how to deduce, okay, how is my sleep rate. Okay, we aim to know, okay, we know that gamma will be different from zero, how we can express our gamma as a function of the stresses or the strains, right? So the condition when gamma is larger than zero, if gamma is equal to zero, there's nothing to deduce. When gamma is equal to zero, we must have f dot equals to zero. F dot, by the chain rule, is the derivative of f with respect to sigma by sigma dot. And sigma dot, okay, we know that is by our linear elasticity assumption whenever in the linear regime, or whenever we have plastic strains, then it means that that must be proportional only to the elastic strains rate. So we always have this relation between the rates. Okay, so it means that my sigma dot is equal to epsilon dot, but epsilon elastic dot is equal to the difference between my total strains and the plastic strains, right? So this must be equals to zero, and the sign of sigma by the Young modulus and epsilon rod. But whenever epsilon p, remember that we said that in order right here that my plastic strains are equal to sign by the sign of sigma, in order to distinguish whether we are on the top or on the which two of the boundaries that we have of my right. So whether we are here, so the sign of sigma is positive, or the sign of negative of sigma is negative. And we may have that my plastic strains may be also positive or may be negative. So in that conditions, we always have f dot equals to zero on that on those locations. Okay. So this allows us to say this must be equals to zero. So this means this is a sine squared is always one. So in total, we have that gamma, and we remove the Young modulus, can be cancelled. Also, we have gamma equals to my sine of the stresses multiplied by the total strains that we have. Okay, so this is writing my sleep rate, or gamma, as the sine by the total strain. So what does it mean on our stress strain diagram? So that whenever I'm moving my total strain, all the strains that I'm beyond this point, all the strains that I'm increasing or I'm applying, they all go to my, on that branch, they all go to the plastic strain rate. Okay, and in fact, all my plastic strain rate is going to be my epsilon dot. So all the strains are going to be plastic. Okay, so on that regime, what I increase as a strains is the same as what I increase as plastic strains, and the same also having here. Okay, there's no sign or nothing involved in that relationship. And on that regime, of course, if this is equal to the total strains are equal to the plastic strains, it means that my elastics are equal to zero. Okay, so this is whenever we are at the boundary. Okay, sigma belonging to the boundary of my admissible domain, meaning that my f of sigma is equal to zero. Okay, whenever we are with gamma equals zero, so either we are on that branch or we are leaving the boundary. Okay, so in that case, gamma is equal to zero. If gamma is equal to zero, we mentioned that epsilon p is gamma by the sign of sigma. So if gamma is equal to zero, then all my plastic strains are not changing, and all the strains that I have are just elastic. So either all my strain rates are equal to the total strain rates, or either this is happening here, but maybe also it also applies whenever we are on those regimes. Okay, in here, or when I'm unloading, parallel to that slope. This is the assumption that we made. Okay, so on those two branches, what we have is that there's no change of plastic strain, and all the changes on my total strain that I have are due to the elastic strain rate. Okay, this is what is happening in that case. Okay, while this is what is happening in this other case. Right, so we know how to compute our gamma when it's different from 0. Okay, and we express it through the total strain rate. Okay, that we have on the upper regime. So in total, now we have all the ingredients, and we have sigma dot. This is the same as sigma dot equals to E by my elastic strains. This is what we know, and we write in a strain rate form, because this is not true if it's not on a strain rate. We are not anymore on my elastic regime. That might be true only on the non-strain rate form when we are on the first branch. Okay, then in here we have that it's also true. But in other unloading, we can also only write it, generalize it, and rate form. Okay, so it's a sort of generalized Hooke's law where we need to remove the plastic and take them into account, the plastic strains. Then how the plastic strains are expressed as a function of my sigma and gamma, which is this slip rate, and we have this constraint. Okay, so it means that f of sigma must be always negative. Okay, and there's this persistency condition that we have here, and this is a Kariusz-Kontruker condition due to the constraint that we have. So that would be in 1D. We are saying how the stresses are related in rate form, and we have one differential equation because we have the derivatives of my plastic strains, which are also included here, with respect to the stresses which are in rate form here. So this is a set of differential equations. In fact, it's an ODE, a system of ODEs. Okay, with some constraints. F of sigma smaller than or equals to 0. Okay, so this is the constraint. Okay, this is called the flow rule because the plastic strains, when they rate, they are called also the plastic flow. Okay, and it's a flow rule of how the plastic strains relate. We know how the elastic strains relate to the sigma. Okay, this is what we have here, but we need to specify how the plastic rate also behave here. So this is the constraint. In fact, is actually here. Okay, and these are the consequence of dot of that constraint. Okay, so if we would like to extend that for not 1D or more dimensions, is exactly very similar. We have that we need to satisfy that, which is something like this. Okay, this must be true at all times, and how we need to specify that in multiple dimensions. So we have something similar. Okay, that is proportional to the rates, like we have in linear elasticity. We have the total strain rates also, and that would be our elasticity tensor of fourth order. Okay, contracted by the total strains minus the plastic strains. So it would be something very similar to what we had before. Okay, this is Cauchy's law, that it's always true, linear, nonlinear, plastic, damage, etc. And we have this constitutive law in that case, and in addition we need to specify, okay, how my strain rates are related to the stress. So we have a constraint that now is a function that goes from R to R in that case. Okay, in here we will write in a similar manner. So we have a function that instead would go from R6, okay, if the stresses are symmetric, and we still assume this. So we have 6 components, independent components, okay, and we take scalar values and we impose that to be. We will see how this extends in multiple dimensions in the next session. Okay, and so we have this constraint. You have this generalized Hooke's law because we have the plastic strains that we have in rate form, but this is our equilibrium, Cauchy's equations in statics, in dynamics something similar but with the inertial term also, and we need a flow rule, which instead of that we will have something like gamma and the derivative of F with respect to sigma. This is associated plasticity. Bear in mind that the sign of sigma with that F is nothing else than the derivative of this function with respect to sigma, right? This is the sign of the derivative of the absolute value of the stresses. Okay, so we would replace that by that. So that would be the problem in R3. Okay, we will have the problem in 1D. Okay, and that would be in 3D. Okay, or 2D. Okay, but there's no any substantial change. The main idea is that we need to generalize our Hooke's law with some plastic strains that we need to tell how they are given. All right, so now this set of differential algebraic equations needs to be solved numerically. This is which type of problem we have, how this is formulated, and now we need to solve. We have a differential algebraic equation, which is given by this relation. We have different numerical schemes that we can adopt. We know, and we have done some of them. Okay, we will see the one to choose. There is, okay, a way to formulate the Kuhn-Tucker conditions. This is that sigma by f of sigma must be equals to 0. This is our Kuhn-Tucker conditions. And one way to efficiently compute, so we will, in order to use our rate form of the constitutive law, so we will need to compute, so to say, our trial function first. Okay, let's assume that we are with a given value of my stresses, and let's see if for those this assumption of elastic prediction, we are not assuming, we are assuming that epsilon p is equals to 0. Okay, so we, instead of the elastic strain rates, we are just including the plastic strain rates. We are just excluding them because they are just we are including, I mean, the total strain rates. Okay, so we predict that our we are going to go, so we don't know where we are in our diagram, so we may be here or maybe here. So linear assumption maybe, or maybe we are at that point. So we are assuming that we go always elastically according to a slope of 1e. We don't know where we are. So let's assume that it's fully elastic, and we check, are we in our elastic regime? Are we here in our point A or point B? Okay, so then our assumption is correct. Okay, then my strain rates are equal to my trial of the stresses. My stress rates are equal to my trial, my assumption. Okay, if it turns out that I am at the boundary, this is point C. Okay, then of course I need to do some correction. It cannot be that my stresses are going to increase. So the total stresses should be equals to 0. Okay, this should be equals to 0 because I'm at the boundary, and then at that point my f of sigma, also f dot, should be equals to 0. Okay, so from that point, so this is in fact what we are assuming is that f dot equals to derivative of f with respect to sigma, okay, by sigma dot should be equals to 0. F cannot increase because it's already 0, so f dot must remain equals to 0. So it means that sigma dot must be equals to 0 when we're writing that, and from that we deduce the value of gamma. Okay, so an efficient way of respecting our Kuhn-Tucker condition or respecting that f of sigma is only equals to 0 whenever our gamma is larger than 0, and that only we're going to have different values f dot different from 0 when gamma is equal to 0. Okay, so way of checking that. And that will be used also for in our scheme. Moving forward, we mentioned that we have this differential equation which says sigma dot is equal to epsilon, so this is all in strain rates. Okay, but we have a differential equation that says that my epsilon p dot is equal to gamma by the sine of sigma. Okay, this differential equation, we can model that with midpoint rule. Okay, that would be the general scheme. Note here that we have the ends on the top left. This is awkward, but in plasticity community, that's the way it was written, and it has kept so. So whenever we have this theta n plus 1 x, it means that we have x at time n plus 1, or pseudo time. Okay, we don't have time dependence, but we have rates. Okay, so we not have, we're talking about rates, although we don't have time explicitly. Okay, but we are going to discretize on time our x. Okay, so we have the generalized midpoint rule, so things evaluated at n plus theta. Okay, and they're weighted by this theta parameter. Then we have forward Euler, which means like theta equals 0, so things are moving forwards according to the derivatives. So this is equivalent to xn plus 1 minus xn divided by delta t equals to f evaluated at n. Here is the same thing backward, but things evaluated at n plus 1. And the midpoint rule is theta equals to 1/2, so it means that things are evaluated at n plus 1/2. Okay, the one we are going to adopt, in fact, is this one. Okay, the backward Euler. We know this is forward Euler. We've seen that in dynamics. This is conditionally stable, so we may have instabilities, and we don't want to mix numerical instabilities from any instabilities we may have. Okay, plasticity problems may yield unstable results, but they are physically unstable. Okay, when we have our things, regions of our domain plastify, we may have collapse and means an instability, and we want to mix numerical instability from the physical stabilities. So the backward Euler method provides at least this unconditional stability, is first order, which is good enough for most of the applications. So, and we don't need to go for the midpoint rule, which is a little bit more complicated because we have this evaluation at the midpoint of f, and our derivatives will be a little bit more complicated. So with this first order, it's good enough for most applications. We don't need to go to the second order. So how does apply for our systems? So it means that our epsilon at n plus 1 p is going to be at epsilon at p. We keep the ends top left and the n plus 1s as well. So we have top right for the p's. Okay, and this must be equal, according to that scheme, to delta t by gamma, okay, at n plus 1 that we will have, okay, and sigma and the sine of sigma at n plus 1. Okay, and we assume that gamma is gamma at n plus 1 already. Okay, so this is our actual implementation of the backward Euler for that differential equations that we have, and we need to solve that the scheme that we have with this time stepping that we have defined. Okay, how this is actually implemented. Okay, so the general problem is that we have some values that we know. From that, know that we also know the elastic strain, which is the difference of the two. Okay, so we have that, and we apply a given increment. This is also input of total strain, and we are thinking of a system like a benchmark that we apply at a given strain. Okay, so it's displacement driven or strain driven problem. We apply a given strain, total strain that we have, or in terms of rates would be advancing a delta t. Okay, and the aim is give me a scheme, and we are using the backward Euler that we just mentioned in order to get the new stresses, the new total strains, and of course the new plastic strains. And from those, again, we can deduce also the elastic strains that we need. Implicitly, we had a given value of gamma, and here we should be able also to compute the new values of gamma, right? So this is the idea of the scheme that we're going, or the methodology we're going to check now. We said this is the increment, the total strain, this is input, so we also know that, okay, everything should be true. So things that should be respected at the end of the step is that my stresses should be equal to, and this is in terms of rate, okay, that the rate of the stresses should be equal to the rate of the strains as well. And okay, so we're going to call this delta t by gamma n plus 1 and the increment of gamma. Okay, and with that we remove delta t and the n plus 1s, and we simplify our notation and the writing, right? And we should also have that the plastic strains, this is our backward Euler scheme. Remember, this is a consequence of what we chose wrote. So my plastics divided by delta t, okay, should be equals to my gamma and everything evaluated at n plus 1. Okay, so the backward is giving backward Euler scheme is giving me this relation between the plastic strains and the sigma, right? Restriction. So we want to satisfy this condition at the end of the step, right? And my delta sigma also should be positive or equal to 0. Gamma is always positive, cannot diminish. Okay, so delta gamma must be always positive as well. Okay, and this means that delta by f is a current condition should be equal to 0. So whenever delta gamma is equal to 0, then is when f can be negative. But if f is different from 0, then this must be equal to 0. Very similar in a discrete form what we had in our continuous with system of constraint ODEs. All right, how do we proceed? So we do in a similar manner as we with a trial value. Okay, so predictor corrector strategy means let's assume that we are somewhere here. Okay, and we are going to go through a step. Okay, this is my and the total strains, and these are my stresses at the previous time step. And let's assume that we can do that step forward, and this is the total strain, and this is given. This is, we said that it's a strain driven, so this is data that they are given, and we want to know which are the new stresses. Okay, what we are assuming here is that my stresses go linearly through a slope of 1 over e, with slope of e. Then this is the assumption. Okay, we predict and we assume linearity, so it means that the strain that I have, these are my plastic strains trial equal to the previous that I had. Okay, so it means that this was my my previous step. We had, of course, that relation must be satisfied that my sigma was equal to n total strain minus the plastic one. Okay, so if we had that this is equal to the plastic one, okay, that we had, the plastic strain is equal to what we had in the previous plastic step. So when this is equal to the what we had plus this, the difference of these two creates this value, and then we are left with delta epsilon by the Young modulus. Okay, so this is given the same stress that I had plus E by delta E, which means going up to here, and that's my new stresses. And then we check the F trial, which is by the definition, okay, the stresses minus the sigma y, which is given here. Okay, so if this is, let's check if this is smaller than 0, so it means that we are still, our step is short enough, okay, so that we are inside our elastic regime. And delta gamma, this assumption of delta gamma equals to 0, that's eligible, so that's correct, and we can move on. Okay, so it's just incrementally elastic step. In that case, what we are doing is that we go from that point to another point in our elastic step. Okay, we will have this at n and this at n plus 1. Okay, and our sigma trial is fine. That would be sigma trial that we have at that point, that we can assume this here. Then let's imagine that we have gone from that point, like in that example, that my n plus 1 trial, F trial, so we have top left, top right, top right. I think there's nothing on the bottom. On the bottom right we have this trial, and on the bottom left I think there's nothing, luckily, because that would be too confusing. Okay, but we still have room for adding something here. So this is larger than 0, like in this case, and this is forbidden. Okay, so this should not be allowed. So let's say something, we need to correct this value. What we are going to do is to project and correct our value of sigma going to admissible domain. So the total strain should be the same, but on doing that step, we need to know how this is going to be corrected, how my plastic strains are also going to be corrected. Okay, and how are we doing to do that? So my new F of sigma for my new stresses, this should be equal to 0, because the trial was not has gone beyond the admissibility domain, so we need to impose this condition, right? Okay, so let's correct. So what do we need is saying, okay, we this is our backward Euler, and this is a discretized form of epsilon p equals to gamma sine of sigma. Okay, and this is a discretized form of epsilon of sigma dot equals, but not in rate form, okay, of our constitutive law. Okay, we have this is, but if we multiply everything by delta t, okay, we will have that sigma n plus 1 must be equals to E by the difference of the total strains minus the plastic ones. Okay, that should be our new stress value. Okay, so Young modulus by the new total strain, this is my total trial value. Okay, this is my assumption. Okay, this is what I tested. Okay, and we have this remaining. Okay, but including this epsilon n plus 1 p that we have here, it's equal to our epsilon n p that we had. Okay, this is equal to the trial minus. Okay, I'm skipping one step here, but I think it's everyone keeps on. We have this is epsilon e minus epsilon p. Okay, and this is n plus 1 sigma trial. Okay, and that's what we are keeping there. So we are left, in fact, with this second term here that is being multiplied by the Young modulus. So all that here is what is going here multiplied by the Young modulus as well. Okay, then my sigma n plus 1, this is equal to the absolute value of sigma by the sign, by its sign, right? So we put that in a no. We have the sign of sigma n plus 1. We want to get rid of this. So let's write this n plus 1 as, okay, as n plus 1, the modulus by the sign of n plus 1 sigma, okay? And we put it there, and we gather that to the other side as well. So we are left with common factor of the sign of sigma n plus 1, and that is equal to, we had this absolute value plus E by delta gamma, and we have this our sigma trial that also we will write in that manner, the absolute value multiplied by its sign. So let's compare here signs and the modulus. If we compare the signs, so it means that the sign of my new value, sigma n plus 1, is the same of the trial. So the assumption was correct. So at least the direction from here, assuming that we are going to that value, so it means that our new sigma n plus 1, that is what we want to compute, okay, is similar to the sigma n plus 1 trial that we had here, okay? So at least the two are on the right, with the right sign, going upwards, okay? Then we, this is a total stress, this is given, so this is also, we know this value, we know this one, and now we try to deduce which is the new delta gamma, okay? So the new delta gamma gives us comparing the modulus. So this absolute value, this is positive, so it means that this sign must be equal. And now let's compare what we have inside the modulus. Okay, the modulus of sigma n plus 1 is equal to the modulus by delta gamma by the modulus of the sigma n trial. So from here, we deduce what is our delta gamma by imposing that that my f, okay, we impose that we must remain in here, so it means that my f n plus 1 sigma must be equal to 0, and f by definition, we know its absolute value is minus sigma y, okay, and sigma n plus 1, the norm, we had it also here, so we replace and we have delta gamma. So f, which was positive here, f n blank trial of our sigma n plus 1 also trial, okay, then we had this was non-admissible, that was larger than 0, and what we do is correct it by dividing by the Young modulus. This is what is giving our amount of delta gamma, okay? So in fact it means that from here all this strain is elastic, and all this strain that we have here is going to be plastic. In other way, this branch here is going to be our delta gamma, okay, which is given to be which is going to be the increment that we have in our plastic strain as well. In this case, everything is positive, so we have no sign associated to that. Okay, so we are reducing our f and denoting by this delta gamma as, okay, the reduction that we have to do to our f, or you have to remove all these strains. They are not elastic, that was the initial assumption, but it was just elastic up to here, and up to from that point was plastic. So once we have our delta gamma, then it means that we know how much is going to be increased our delta p. From this delta gamma, our plastic strains are going to be those that we had previously by the sign of n plus 1 sigma. Oops, I'm moving a little bit. Okay, epsilon 1 sigma, epsilon, this is the sigma n plus 1 what we just computed, okay, and its sign that we had, which is equal to the sign of the trial that we had, okay. So we know this value, and now our elastic strains n plus 1 is the total one that we have, is this value minus the one that we have just computed, right? So with that we have everything that we wanted. Once we have delta gamma, then we have the plastic strains, and then we have the elastic strains, and we also have the total stresses. We have the modulus of the total stresses also from here, and the sign of the total stresses. Okay, should be through the sign, which we do have, multiply, this is the sign, multiply by the modulus. Okay, so we do have from here in total the total stress. Okay, and that's what we have shown done just here. That was the first. This is the backward Euler. Okay, and this is from the equation that we had. So this is the same of deducing that from here, from that amount that we had, or that, or just alternatively we can have its sign by its modulus, or its modulus n plus 1, okay, by the sign of n plus 1, which we do have. Okay, any of the two, which is the same of the trial, just to have it have the same sign. So either here or either that one. Okay, so with that we have the how to compute in one step the two of them. Okay, we have also very similar equations for the case, okay, when we in fact we have hardening plasticity, which means that we allow that to increase also, that is not anymore flat, but we have an increase also of our admissible domain. Okay, that's sigma y, and as the stresses increase, okay, or as the strain increase, so we do have an increase of our domain. Otherwise, we have that f depends the absolute value minus sigma y was what we had before, but now this is proportional. This sigma y also is increased by something proportional to a modulus, yes, which is modulus to alpha, where alpha is the amount of plastic strain. What is the amount of plastic strain? So this slip rate that we had, so this gamma. So when gamma is higher, so it means that this is also increased through this parameter alpha that we place it here. So the objective here is to have a parameter that tell us how this factor is going to increase. Okay, so a function gamma, we know that epsilon p rate, so if this increases very steadily, so it means that also this sigma dot, so what we have is that our sigma dot is, if the sign is constant, so it's also constant to the plastic strain rate. And this is what we are including in here, is this alpha parameter. This is exactly the same that we had, so the only modification that we have is this factor of the yield condition. So it means that my domain that we had for sigma was sigma y and minus sigma y, and that was my admissible domain. But if I keep increasing, this should be here. Okay, if I keep increasing my stresses, so my domain is enlarged at that point. Okay, when I have a certain amount of plastic strains. Okay, so this has been enlarged, and now my admissible domain that initially was this 0 now has been enlarged on the two sides, because this affects the absolute value. So this is maybe a new value of my invisible domain for that point that I have here. Okay, so now this interval is larger and larger as my plastic strains keep increasing, and that's a modification that we do. So we look at how the backward Euler can be also applied here. This is the same type of problem, so similar to perfect plasticity, but with a parameter, okay, that keeps increasing this value. So with that, we end this first session on plasticity, and we go to the numerical integration of these other equations. I suggest as an exercise for the next session to deduce how our scheme would be modified. There's no much to modify. In fact, it's just sigma y, which is replaced, or my f, which is replaced by this, okay, by this extension, and also we have this backward Euler being applied here, and now we need to apply Bicart Euler also here. So meaning that my n plus 1 alpha minus n elf divided by delta t should be equals to n plus 1 gamma. Okay, this is the backward Euler corresponding to that scheme. The one for this one is exactly the same that we had before, but we need this additional numerical integration for dot differential equation. So we'll continue in the next session. Goodbye.